Okay, okay, we will start. I don't think others will join. Only two students are there, Hers and Manish. Hello, am I audible now? Hello, Hers, am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay, okay. So I will share my screen and then we will start solving the question. See, if you have some doubt, then I am sharing my mail ID. You can send your doubt like in my mail ID, so that in that I will reply to that. So I'm sharing my mail ID with you. Okay, so I have shared my mail ID. So if you have some doubt or some some question, some technical doubt, then you can share with me. But before asking the doubt, you try to solve that question. Whatever it is wrong, it is fine. But I want some input from you. Don't ask I'm not able to solve this question, so you solve it. Don't ask like that. You try to solve. If you are getting the wrong answer, you send the wrong answer, wrong solution, and then we will discuss. Okay, so last class some questions were remaining. So first we will discuss those questions, and after that we will move to the week 6. मेरा मीटिंग चल रहा
पैसे देगी
है क्या?
ये तुम्हारा है कोई आंटी है बाहर ब्लू डॉट से कुछ मंगाया था
अच्छा, ये हमारा है, ठीक है.
1 मिनट के लिए बाहर चले जाओ बोल दीजिए
Hello. Yeah, guys, please give me 1 minute. I have some urgent work. Please give me 1 minute. I will be back. Anna, my meeting is going on. This is our lab item. Can you go and see? Go and see.
नहीं ये तो यहीं पे उसको एक बार बोल दे कि हाँ मैंने ले ली रिसीव कर लिया
What should I do? Okay, okay, I am waiting for. What should I do? Hello? Yeah, yeah, yeah. Now we can start. Okay, so I think these two questions were remaining. See, Rahul, sorry, Manish. See, these two
Yes, sir.
question was like last two question was remaining, right? 10 and 11.
Yes. Yes, sir.
Yeah, yeah. So can you try to solve question number 10?
Just a sec, sir.
Yeah, yeah, yeah. Harsh, are you there? Harsh Patel, are you there? Manish, are you trying to solve?
Yes, sir.
Yeah, yeah, yeah. Question number 10. Okay, okay. Okay, Manish, see, simple.
Sir,
See, yeah, yeah.
sir, I
Sorry,
am unable to
what you
solve
are
the
saying?
question, sir.
Sorry?
Sir, I am unable to solve the question, sir.
Okay,
What
so
the
so what?
formula used in this question, sir?
Yeah, yeah. Question number 10. Can you answer the question number 10? Question number 10.
Sir, please tell me the formula using this question.
See, it's a very simple question. You just need to find the order with respect to the fuel and overall order. So just you sum this, the power of this. See, suppose that this is the equation C6H6 is
Yes,
reacting
sir.
with the oxygen. So see, these two are the products. So this is the the rate of change of the product, like C6H6. So the order is the power of fuel is like this 0.3, that is the order of fuel, and overall is 1.6 plus 0.3, so 1.9, that's it.
Okay, sir. 0.3 and 1.9.
Yeah, 0.3 and 1.9.
Okay, okay, sir. Just a second.
Okay, so try to solve question number 11.
Just a second.
Yeah. Manish, try to solve question number 11. And see the time
Yes,
for.
sir. Yes, sir. I'm trying, sir.
Yeah, see, I will give you a hint. The characteristic time is the time at which this.
The formula is used in this question 1 by k of f in bracket C4 H8.
Wait. I will write it. Uh, yeah, question number 11. Yeah, how you are solving?
Yes, sir.
Yeah,
The formula is used there. T is equal to 1 by k of f.
this is characteristic time, right?
Yes, sir.
1 by k, yeah.
uh, Multiply by 1 by in bracket 1 by C4 H8. Sorry, sir. Sorry, sir. 1 by C4 H10.
Yeah. No, see, the characteristic time is, this is unimolecular reaction. So the characteristic time is T characteristic is equal to the 1 by k. Basically, the characteristic time is, suppose that X concentration of X of C4H10 are the time at which concentration of C4H10 upon initial concentration is equal to the, this is initial concentration is equal to the 1 upon E. The time at which the concentration of the product upon initial concentration is equal to the 1 upon E. That will give the characteristic time.
Okay, sir.
Now see, just use this equation and you solve it. See, suppose that D, wait, see here you just simply use the formula. See simple, that's it. D, this is, this minus sign will come because see this is decreasing with time. So now just see d, suppose that x is the concentration, dx upon dt is equal to the minus k into x. That's it. Now you find x upon x naught, the time at which x upon x naught is equal to the 1 upon e. Simple you can find now. This is dx. So concentration at the time t. So x is the concentration at the time t. So dx upon dt is equal to minus k into x. So you need to find x by x naught. At the time, you need to find the time at which x by x naught is equal to the 1 upon e. Okay, I will solve it. I will solve this. Manish, should I solve it or you are trying?
Sir, solve it, sir.
Okay, so see this dx by dt. What is x? X is the concentration at the time t. Dx by dt is equal to the minus k into x. If you bring x, if you bring x to the left hand side, so dx by x is equal to the minus k into dt. Now you just integrate.
Yes, sir.
Yeah, 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 yeah. It will
Then
come
it's
ln
log of x.
log x by log x. It will come log x. Yeah, it will come log x
Yes, sir.
is equal to the see.
That's true.
Yeah, it will come log x is equal to the minus k into t plus c, right?
T plus c. Yes, sir.
Yeah. So this is this base 10 or base e?
Base e, sir.
Base e, right? So at t now we need to find the constant c. So at time t is equal to the 0, the the concentration x is x naught, right?
Yes, sir.
So we will get log x naught is equal to the c. Now you replace c with log of x naught. You will get
C with okay, log x naught. ठीक है,
yeah.
sir.
You will get log x is equal to the minus k into
So
t plus
kt
log
plus
of
log of not x
x
naught.
naught. Now you bring this log x naught to the left hand side.
Then log x upon x naught.
Log x upon x naught
Not
is equal to the
is
minus
equal to
kt.
minus of kt. Yes, sir.
Now you need to find the time at which x upon x naught is equal to the 1 upon e.
Okay.
This will be log, yeah, 1 upon e. is equal to the minus kt. Now what is log 1 upon e? Minus,
Log 1 upon E.
yes,
minus 1.
minus 1 is equal to the minus kt. So the time at which t is equal to the 1 upon k. Now you
K.
just you calculate 1 upon k. Time constant t is equal to the 1 upon k. What you are getting, log 1 upon k, 1 upon 4 into 10 to the power 5. So it will be 0.25 into 10 to the power minus
Or
5.
minus 5.
So 2.5 into 10 to the power minus 6, right?
Minus. Yes. Yes, sir.
So this will be 2.5 into 10 to the power minus 6 second, right? Say 2.5 into 10 to the power minus 6 second. Time, right? Time is second, right? Time in second, 1 by k, you are saying.
Yes, sir.
So it will be second. So this is the correct answer, and they have given the answer in milliseconds. So it will be 2.5 10 to the power minus 3. So this 0.002.0.0025.
Yes, sir.
See, because see, they have given the answer in millisecond. Yeah. See, this answer is in millisecond. Like they didn't mention like the unit, but the correct answer is 2.5 to 10 to the power minus 6 second, or like this is 0.0025 millisecond.
Millisecond. Yes,
Yeah,
sir.
yeah. So this is week 5. Now we will move to week 6 content. Okay, okay. So try to solve question number 1.
Remains constant.
Remains constant. Okay, remains constant is not correct. See, this is like how the incompressible reactive flow is defined. So it's not like if it is changing with temperature. See, the definition of incompressibility is del rho upon del p is 0. It is not changing with pressure. See, if you see the definition of incompressible fluid flow, incompressible flow, then del rho upon del p is equal to the 0. Means it is not changing with pressure.
It changes with temperature.
Changes with temperature, that is correct answer. Changes with temperature, remain constant is not correct. It changes with temperature, changes notably, this is incorrect. Same as the mixture, this is incorrect. Okay, so question number 2.
Same as pressure.
Same as pressure. Yeah, same as pressure, that is correct answer. Same as pressure, or we can say compression in nature. Compression in nature. What is the mistake with this answer?
Sir, I think it is tensile in nature.
Uh, See, the answer they have given is tensile in nature, but how in a fluid element you will apply tension? I think this answer is wrong. The answer they have given is tensile in nature. I don't know on what basis they have given, but up to my knowledge, this is wrong. On how in a fluid element you will apply tension?
Yes, sir.
Sir, actually the pressure is taken normally perpendicular to the surface, and in both the cases, on the one side it is in a x direction, on another side is in minus x.
See, basically you are saying, wait. Basically you are saying, suppose that if the pressure is applied, this is the pressure. So you are saying this is a fluid element. This pressure is applied. Now, yeah, you are saying in other side it will be like this. You are saying that, right? Hers, are you there?
Sir, it is exactly opposite. The arrow should be opposite.
Yeah. That is, see, I have written opposite only, right? See, this is fluid element. Just consider fluid element, and now this is pressure. This is acting. Pressure is acting. So now here you are saying exact opposite, right?
No, on the outer surface itself, it should be in the opposite direction. Actually, top arrow it should be at the top face, and the bottom arrow should be at the bottom face. Yeah, this is something how the sir has dictated in the lecture.
Fluid element he have dictated like this.
Yes, sir. It was dictated like that only in the lecture.
Bro, I don't know. See, I have to check, but see, I have never seen like tension in fluid element. Tension in fluid element for me doesn't make any sense. So I have to check, but the answer they have given is tensile in nature. So, but the correct answer they have mentioned is tensile in nature, but I don't know the exact answer. I will check. Maybe I will discuss in the next week, but I don't know exactly. Like I have to check the video. Okay, guys. So, sorry for that. I don't know the answer, but up to my knowledge, it should be compression in nature or same as the pressure. Both are correct because it is normal stress acting on fluid element is. It should be compression in nature up to my knowledge. But okay, so leave it. We will move to question number three. So, question number three. See, I will discuss this question next week. Maybe I will discuss with that Raghavan sir, or maybe some other TA. I will discuss this question, and after that, we will come up with solution. So I don't know the exact answer question. Question number two. On what basis they have written tensile? I don't know. So question number three. See, basically, see, it is like suppose that in species transport there are two ways by which species are transporting. Like one is bulk transfer, other is due to diffusion. So now you can answer the question number three.
Sum of diffusion plus and entropy of an individual species.
Enthalpy of individual species. Yeah, and plus bulk plus bulk plus
Yes,
energy
sir.
flux due to bulk.
And yes, sir. Yes, sir.
So the answer should be both A and B, right?
Yes, sir. Yes, sir.
See, basically that species transport two different ways. Other one is due to bulk transfer, other is due to diffusion. So it both answers should be correct, right? Okay, so the answer is sum of A and B. So both A and B. So now question number four. Try to solve the question number four. A substantial derivative, total derivative, or material derivative both are same. Substantial
So,
derivative, total derivative. Yeah.
Sum of local and convective derivatives.
Yeah, yeah, yeah. What about Manish? What is your answer?
Yes, sir.
Local
Sum
and
of local and
convective derivative.
local time and
Yeah,
convective
yeah, yeah.
derivative.
So basically, see, just suppose that maybe uh, this is d, capital D. This is not del. Du by dt is equal to the del u upon del t plus u into del u upon del x plus v into del u upon del y plus w into del u upon del z. So this is local derivative and this is convective, and this is material derivative or total derivative or substantial derivative, you can say. Okay. Okay, question number 5. Lewis number is defined as the ratio of Lewis number. Generally, in many cases, we consider Lewis number is equal to the 1.
Thermal diffusivity to mass diffusivity.
Thermal diffusivity to mass diffusivity. Yeah, basically,
Yes, sir.
yeah, yeah, yeah. So
B.
alpha upon,
Thermal
yeah, alpha upon D.
B.
Thermal diffusivity to mass diffusivity. Okay. The governing equation of the conserved scalar is linear, has a definite analytical solution, has no source term, is always steady.
Sir has no source term.
Has no source term, it is covered in the lecture. So yeah, that is true. Now question number 7. This is this is also like covered in the lecture. So question number 7.
Chemical time is greater than flow time.
Chemical time is much greater than flow time. Okay. So if the like some transport governing, if the combustion is transport governing, then what will be the answer?
Flow time is much greater than the chemical time.
Yeah, yeah. What about Manish? What is your answer?
Sir, I have no idea.
Combustion is kinetically controlled when the chemical time is equal to the flow time. Flow time is much greater than the chemical time. Reaction is infinitesimally fast, and flow time is much less than the chemical time.
I think, sir, flow time is much less than the chemical time.
Yeah, yeah, yeah. See, basically they have defined two, like it is one is kinetically controlled. See, suppose that if the chemical time is much greater than the flow time, then it is kinetically controlled. If the flow time is much greater than the chemical time, then it is transport controlled. Okay, okay,
Okay.
okay. So try to solve question number 8. Manish and Hers, both of you, try to solve question number 8. Just use conservation of mass, that's it.
Point zero 0.01.
0.01. Okay, 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 okay. See, it may be correct, but I want the answer from Manish.
Just a sec, sir.
Yeah, yeah. You just use conservation of mass. Just that's it.
Sir, 0.02.
0.02. Okay, see. Okay, so first thing, Harsh, you tell me how you are getting 0.01.
Sir, it is the mass which is coming in is 0.03, coming out is 0.029, and generation is 0.01.
Okay, mass coming out is 0.3 and mass coming out. So this is in and this is out. So total mass in is equal to total mass out, right? If no, we cannot write total mass in plus accumulation is equal to total mass out, right? Total mass is simple, mass in,
Is equal to mass out.
mass in plus accumulation, something is
Oh,
accumulating, right,
yes, sir.
is equal to the mass out. If there was, if it is a steady, if it is a steady process, like steady means it is not changing with the time, so nothing is accumulating, so then in that case mass in is equal to the mass out. But in this case something is accumulating, so mass in plus the rate of mass in plus the rate of accumulation is equal to the mass out.
Yes, sir, got it now. It is 0.02 only.
Zero point 0.02. Okay, okay. So can you tell me how you are getting 0.02? Mass in is equal to the 0.3, right?
Mass in minus mass out, that is 0.01 plus mass 0.01 is already being generated in the system. So total is 0.02.
Yeah. Now 0.02 you are saying. So we need to find mass, and some mass is 0.3. Where should I add 0.01? Here or here?
It is at the left hand side.
Left hand side. Left hand side. Okay. Zero point 0.01. Yes. Plus accumulation, right?
Yes, sir.
So yeah. Now what is accumulation?
It comes to be zero then.
Wait. Total mass in is equal to the 0.03 plus 0.6. This vapor is generated, so it is 0.001 plus accumulation total. Give me a minute. Plus accumulation is equal to the total mass out. No, here I think I have done some mistake.
Sir, it is simple actually. Sir,
Yes.
let us not consider the accumulation, that generation in the equation. Mass in minus mass out, that is actually added into the system, plus the system is adding 0.01 vapor itself. So total generation will be 0.02.
No. See. I'm not getting. See, wait. See, here it should be mass in is equal to the mass out plus accumulation. Just wait. It should be mass out plus accumulation. It should be like this. Do you agree or not?
Now it is okay, sir. It is fine.
Okay, now it is fine. Mass in is equal to the mass out plus accumulation. The rate of mass in, the rate of mass in, mass out plus the rate of accumulation. Yeah, is it okay or not? Yeah, Harsh.
Yes, sir.
It is okay. So mass
Yes,
in,
sir.
yeah, it is okay. So mass in is equal to 0.3 plus mass of vapor, the rate at which mass the vapor is generating. So that is 0.01 is equal to the mass out is equal to the 0.29 plus accumulation. Yeah, so the rate at which it is accumulating, it is 0.31 minus 0.29. 0.31 minus 0.29. So this will be 0.02, right? Yeah, this will be 0.02. Okay. Okay. So try to solve question number 9.
Excuse me, sir.
Yeah. Yes, yes.
Sir, actually, I'm going to my home, so I will not be available for next 15 minutes or so. I will join. I will be joined as it is, but I will not able to answer the question.
Okay. I don't have any problem, but okay, I don't have any problem. You can.
Okay, so I will be joined as it is, but I will not able to give the answer.
Okay. 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 So, Manish, try to solve question number 9. Just give me a minute. Just. Try to solve question number 9. Manish, are you solving question number 9?
Yes, sir.
Yeah, yeah, yeah. Okay.
पढ़ाई नहीं हो रही बाकी तो
Sorry, I'm not getting. What did you say? Something? Okay. See, I will give you the hint. I will give you the hint, and then uh, first you calculate the amount of the mass of fuel that is entering the mass of fuel that is entering that furnace. First you calculate that. Then you calculate they have given the mass of air, and they have given the specific heat. So with that you calculate the temperature that it will reach. Just Manish, should I solve or you are trying?
सर सॉल्व
Okay, so just you tell me your approach. How did you try to solve? What did you do? Like what you did or something like that. Whatever you have done, you just tell me, and after that I will solve them. See the like we need to find the average furnace temperature. That is something we need to find. So how to approach this question? Just you tell some basic step, and after that I will solve. Okay, okay. I will solve, no problem. See, that fuel is releasing. One thing I want to ask. Okay, let Hers will come after that. I will ask you. Okay, so one thing, it is releasing fuel is releasing 500 kilowatt of heat. 500 kilowatt of heat. It is kilowatt means kilojoule per second, right? Kilowatt means kilojoule per second. Manish.
यस सर
So it is releasing 500 kilojoule per second of heat. 500
यस सर
kilojoule per second.
जूल
Kilojoule
पर
per
सेकेंड
second of heat. Now the mass. Can you calculate the mass flow rate of fuel? Mass flow rate of fuel. It have that combustion of fuel is the standard heat of combustion of fuel is 20,000 kilojoule per kg. What is
किलो
the
जूल
mass?
पर के जी यस सर
What is the mass flow rate of fuel?
सर मास फ्लो रेट ऑफ फ्यूल इज 20,000 किलो
See this see, I can see there is some background music. Can you stop him? Like I can see some background music is there in your place.
सॉरी सर
Yeah, yeah. You tell him to stop that music. Okay, okay. So what is the mass flow rate of fuel? See. You read just first line. In a furnace, a solid fuel block burns, releasing 500 kilojoule per second of heat. Then the standard heat of combustion of the fuel is 20,000 kilojoule per kg. Now and like this fuel is releasing the heat at this rate, then what is the mass flow rate of fuel? See, you are, this is, suppose that this is a furnace and this is releasing the heat at the rate of 500 kilojoule per second, means in 1 second it is releasing 500 kilojoule of heat. So this heat, like this, whatever fuel you are supplying, that fuel must supply this much of heat. So how much fuel is needed to supply this much of heat in 1 second?
20,000.
20,000. 20,000 will give 20,000. Like you are saying 1 kg, 1 kg will give 20,000 kilojoule of heat. So how much fuel is required to get this much heat? See, now see the, see, you read the question one more time. I think you should be answer, you will be able to answer this question. Suppose that in 1 kg we are getting 1 kg fuel is giving this much of 20,000 kilojoule of heat. 20,000 kilojoule of heat. Now 1 kilojoule of heat will be obtained from how much kg of fuel? 1 kilojoule of heat will be obtained from 1 upon 20,000 kg of fuel. uh, see, Manish, is this okay?
Yes, sir.
Now 500 kilojoule of heat. Now 500 kilojoule of heat will be obtained from 500 upon 20,000 kg of fuel. Is this okay? Is this okay, Manish? Is this okay?
Yes, sir.
Now you calculate 500 upon 20,000. What is this? What is this? 500 upon 20,000.
It's a 0.25.
0.25. So it is 0.25 kg.
Yes, sir.
Okay. Okay. 0.25 kg. So this much heat you are getting 500 kilojoule, means they have written 500 kilowatt, means 500 kilojoule in 1 second. So you are supplying 0.25 kg of fuel in 1 second. The mass flow rate of fuel is 0.25 kg per second. Okay. Mass flow rate of fuel is 0.25 kg per second.
Yes, sir.
So now they are asking, the solid has to be heated from 25 degrees Celsius to 350 degrees Celsius for it to release fuel gas. Now to heat this solid from 25 degrees Celsius to 350 degrees Celsius, how much heat is needed? So here you can say that Q sensible to heat the Q sensible to heat the fuel is equal to the, here you can write like for fuel something you can write, so it will be 0.25 mCp into delta T. So Cp is 1.5. What is delta T? Q sensible for fuel, like to heat the fuel from 25 degrees Celsius to 350 degrees Celsius, how much heat is needed? To increase the temperature of fuel,
325. 325 degrees Celsius.
325 into 325. So now you calculate this. 0.25 into 1.5 into 325. 0.25 into 1.5 into 325. So it will come 121 point kilojoule per kg. 120 into 325 mc delta t. It will come 121. It will come 121.875. What is the unit?
1 to 1.875.
1 to 1.875 kilojoule, right?
Yes, sir.
So this much heat is required to heat this to increase the temperature of fuel from 25 to 350 degrees centigrade.
300 degrees Celsius.
Now they are supplying the air at 25 degrees centigrade at the flow rate of 0.3 kg. See, one thing you see here, this is not 0.25. Can you check this? 500 upon 20,000. It will be 5 upon 20, so it will be 0.25. It will be 20,000. 500 upon 20,000. Yeah, this is correct. This is correct. Okay. So now uh, ambient air 25 degrees. Now this air is available at zero, the mass flow rate of air is 0.3 kg per second. Now you consider suppose that just you assume that temperature is let temperature of furnace is T. See, just consider this T. Now you do just energy balance and you will find the T. So how you will do that? See, total heat available is 500 kilojoule, sorry, kilojoule per second. No, see, total heat available is not 500 kilojoule per second. You subtract 500 minus 121.875. Now see, you subtract this sensible heat, so heat available Q available will be 500 minus 121.875. So what this is, minus 121.875, it will be 378.125. Now this much heat is available after sensible heat. So 378.125 is equal to the mass flow rate of air m into Cp of air. They have given this like average Cp. They have considered, take the average Cp is 1.5 mc into this, like whatever product is there inside the furnace, they will reach to the temperature of furnace. Suppose that furnace temperature is T, so air will also reach the temperature at T, and that fuel will also reach the temperature T. So mc into T minus this air, mc into T minus this initial temperature of air 25 plus, now see, this this is available at 0.25, mass is 0.25 plus 0.25 m c into, now this is at T, minus, now you tell me what should be the temperature here. This we have previously we heated to 350, so it was available at 350. Now you Manish, you tell me if it is clear to you. If not, please let me know.
Y- Yes, sir. It's
It is
clear.
clear, right? See, basically, this much heat is 121.875 kilojoule heat is required to increase the temperature of fuel. So we have subtracted it. Now this much heat is available, and now this air will reach at the temperature T, and this fuel will reach at the temperature T. Initially we heated to 350, now it will reach at temperature T. So can you solve this equation to find T?
Sir, what will become in the place of T?
See, that we need to find, right? That is unknown. That is T is unknown. Furnace temperature. T is furnace temperature. See, basically, what what we are doing. Suppose that this is a furnace. You enter like some 0.3 kg per second. This is the rate at which air is entering, and 0.25 kg per second. This is the rate at which fuel is entering. Now we need to find the temperature. You can consider the exit temperature, that like whatever is coming, and that finally the temperature that it will reach, that we need to find. And there is assumption like there is no heat loss from the furnace. This is one assumption. That no, is this clear to you, Manish, what I am trying to say?
Yes, sir.
See, simply in one way I can say you need to find the adiabatic flame temperature. Just in simple we can say that.
PV raised to the power gamma minus 1 is equal to constant.
Manish, what do you think? PV reach to the power gamma?
Minus 1 is equal to constant.
No, no, no. See, you are see like you try to understand. This is not the PV to the power gamma is for no, 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 no. See how you calculate the adiabatic flame temperature. How you calculate the adiabatic flame temperature? See, enthalpy of product is equal to the enthalpy of reactant. That what we do, right? This is what we do when we calculate the adiabatic flame temperature. So we need to find at which the enthalpy of reactant is equal to the enthalpy of product. We need to find the temperature at which enthalpy of product is equal to the enthalpy of reactant. So that what we did to find the adiabatic flame temperature. See here what we are doing. See, suppose that we are supplying fuel, we are supplying air. So that air will reach the temperature of furnace. So the amount of heat that is released from the fuel will be used to increase the temperature of fuel and air. So that final temperature we need to find. Manish, am I clear to you?
Yes, sir.
Yeah. Okay. So can you find T from this equation? Can you calculate T? See, we have done a mistake. See, wait. See that what I'm doing.
Just a sec, sir. I am calculating, sir.
Wait. Manish, we have done a mistake. See, 500 upon 20,000. What will be? What it will be? It won't be 0.25. 500 upon 20,000. 500 upon 2,000 is 0.25.
Yes, sir. It's 0.025.
Yeah, it is 0.025. So now, see, it is 0.025. Because of that, we are getting the wrong answer. It will be 0.025. Just 0.025. So here it will be 0.025. It will be 0.025 mass flow rate of fuel. See, whenever I am doing some calculation, if I am doing some mistake, so you should like let me know that point. Now Q sensible, so it will be 0.025 into 1.5 into 325 Q sensible. Yeah, so it will come 0.025 into 1.5 into 325, 0.025 into 1.5 into 325. So it will come what 12.1875. See, you also like with me, like you also calculate you 12.1875. Now 500 minus 12.1875. So it will be 500 minus 12.1875. 500 minus 12.1875. So 500 minus 12.1875. 500 minus 12.1875. 12.1875 487. So it will be,
0.1825.
sorry, it will be 487. 487.8125. So here it will be 487. It will be 487.8125. Now this is okay. Here it will be 0.025. Hello. Yeah. Manish, are you able to understand what I am doing?
Yes, sir.
Yeah. So simple, you just 487.8125 plus 0.3 into 1.5 into 25 plus 0.025 into 1.5 into 350
Sir,
upon,
excuse me.
yeah,
Sir, should we not convert the temperature in Kelvin?
it is in Kelvin only, right?
25 degree.
See, wait. See, this temperature is in degree Celsius. Wait. See, the thing is, if we are subtracting the temperature, then it doesn't matter whether it is in Kelvin or Celsius.
Sir, what you're telling is actually right, but I think here we are adding up the temperature. I don't think that we may get the wrong answer, because here we are adding up the temperature. Here delta T is
Where we are adding the temperature. Here we
no
are,
in this term 487 point something which is there, no.
yeah, this term.
Yeah, we are adding up the temperature. If the sir, if the consistency is remaining same in case of Celsius, it is fine. Fine. Otherwise, sir, I think we should convert it before.
Yeah, yeah,
Uh,
yeah. That is correct. But see, I think we should get correct answer because we are not adding where we are adding the temperature here. I totally agree with you. We should convert it before, but in this case, we are not adding. We are subtracting, so it doesn't matter where we are adding.
in the last sir, step that you wrote,
Last
uh,
step.
yes, here we are adding up the temperatures. 487.828125 plus the bracket term. I think
See, this equation we are solving here only, right? Wait,
mhm.
wait. See, this equation is correct, right? This
Yes,
equation is
sir.
correct. There is no problem with this equation.
Yeah, it is totally correct.
Now, if this is temperature in degree Celsius, so we should get the answer in degree Celsius, right?
Okay, fine, sir. I think you are right. If we will convert or not, it doesn't
It
matter, I
doesn't
think.
matter, but yeah. We should convert. We should convert anyway. If you want, I can convert it now. But I think
No,
you will
no.
get the correct answer. So this is 350 degrees Celsius. Here it is 350 degrees Celsius, right?
Hmm.
350 degrees Celsius only. Okay, okay. 0.3 0.3 into 1.5 plus 0.025 into 1.5. 0.025 into 1.5. Can you calculate this? Yeah. Yeah. What you are getting? Are you getting this? 1050.
Yes, sir. Yes, sir. Yes, sir.
Yeah. So
Just
this
a sec, sir. Just a sec.
this should be the correct answer. Now 1050.641. 1060. They are
Yes, sir.
asking in Yeah.
It is getting. I'm getting the same.
Okay. So they are asking in Kelvin. So just so if you convert this to Kelvin, it will come somewhere around plus
One
273
one three two three point six four one.
1323.641. It will come like this. 1323.64, 273 if you add. Yeah, 1323. 1323. So it
Maybe 1299. That is
maybe
fine.
1299. Yeah, 1299. 1299 is correct. Basically, I think if you take like this answer is within 5% limit, so that is correct. 1323. So 1299 is correct. Okay, so try to solve question number 10. Okay, see before that, Manish, I want to know like is this question clear to you? We,
Yes, sir.
yeah, yeah, and Harsh, I hope this is clear to you.
Yes, sir.
Okay, question number 10. Try to solve question number 10. This is like easy, little bit conceptual question. We will solve question number 10.
Sir, first of all, we have to calculate the density of the air from PV equal to MRT.
Yeah. See, no, not first of all, you can without calculating the density also percentage of stoichiometric air that has entrant is. See that what we have to calculate.
Hmm.
Stoichiometric air means
It
see
is percentage. So just balancing of the equation, that is more than enough.
yeah.
It is a we can get the actual the theoretical air, and based on the actual condition, we can find out the mass flow rate of fuel upon mass flow rate of air, and
Okay. Okay. Okay.
volumetric flow rate.
Okay, okay. Before coming to this question, just I want to ask you one thing. Like both of you, I want to ask one thing. Suppose that like we solve one question. Just give me a minute. Just one thing I want to ask. Suppose that this is a fuel. This is a solid fuel,
Hmm.
and it is burning. So what is this? Like, if you see a flame, is this flame like this, or the flame
Yes,
is
sir.
like this? Just give me a minute. Just or the flame is something like this, and like there is a vapor and or the flame is like this is a solid cone, this is a solid. What is flame? Is this solid or this is hollow? What I am
Which
saying,
one?
no, no, what I want to ask one thing. Suppose that this is a some solid fuel.
Yes, sir.
Now you see it is burning, so you see a flame,
Hmm.
something like this.
Hmm.
So inside the flame, what is this inside the flame? Is this flame is solid or inside the flame there is a vapor? Like I am asking about this region.
Vapor, vapor.
It is vapor. What about Manish? What you are saying?
Yes, sir.
Yeah, suppose that this is a solid and you see one flame like this. You see one flame. So
Yes.
inside the flame,
Yes.
what is there? Is this a solid? Like inside the flame, there is another flame, or
Sir,
inside the flame,
it
there
is
is
in
vapor?
vapor.
It is a vapor.
Vapor, vapor, sir.
It is a vapor. Or, see, anyway, this is even this wave won't touch the solid. This solid will convert the vapor, like some volatile component will come out from the solid, and that will cover the flame. So if you take one, suppose that if you take the some laser light and you pass through it, so you will see only 2 point, and inside this there is a vapor. Okay, okay. So just I wanted to tell you this thing because sometime some student may get confused. Okay. So come to the question number 10.
Sir, AM upon AO is 400 and
Wait. AM upon AO is 400. You are saying?
yes, sir.
Just give me a minute. So here AM upon AO is 400.
Yes, sir.
Yeah. So AM is butane gas mixture. This is 20
Yes,
20 square upon, yeah, it is
one.
400. Yeah. It is
Okay.
400. Yeah.
Okay. And I think density of the this butane and the air we have to take calculate
Yeah, we have to calculate the density.
from the equation of state
Yeah. From like, yeah. We can calculate from the PV is
equals
equal to
to
the MRT. We can use that. PV is equal to the MRT you will use to calculate the density, right?
or directly we can take the ratio of the two things as the pressure is almost going to remain pressure and temperature are same. Its value depend on the the specific gas constant. Uh, the ratio of it depends on the specific gas constant value.
Yeah. I am getting. Yeah. That is correct. Basically, a specific gas constant, that too, it value depend on the molecular weight, right?
Hmm.
Because a specific gas constant is universal gas constant 8.314 upon molecular weight.
Yes, sir.
Okay. So what answer you are getting?
Let me, sir. It is a butane, no?
Yeah, butane.
It is 2. Density ratio is around 2. Because for our air, it is 0.287 divided by the R of fuel, that it comes out to be 0.143.
Now density of butane P upon R into T. R
Hmm.
is for butane.
Yes.
P and T are same, so density of butane upon density of air is equal to the density of
R,
like
RA
P
upon RB. RF.
into T. So this is air, so density of butane upon density of air, so it will be Ra upon Rb. So it will be 8.314 upon this 28.8, right? Molecular weight of air.
Yes. And you, sir, directly we can take 0.287. RA. And for RB, we have to calculate, and it turns out to be 0.143. It is 58.
C4H10 48 plus 10 is equal to 58. C4H10 butane. So it will be 58. So 58 upon 28.8. Yeah, density of butane upon 58 upon 8 upon 28.8. But I don't think use. Yeah, it is coming
006.
yeah, 2.013. 2.013.
Uh,
58 upon 28.8. Okay, that same thing. But I don't see you need to calculate the density where R is the relative density of the fuel. Yeah. R you have to calculate the relative density. So it is coming 2.013. So R
mhm.
relative density you have to calculate fuel with respect to the air. Yeah, and AM upon A. So it will give the volumetric. It will give you the volume
Volumetric,
ratio.
sir, it turns out to 15.015 meter cube of air upon
15.
meter cube of fuel.
That E. You are saying that E is coming
E
out.
value
Yeah.
15, 0.015.
Point 0.015. Point 0.015.
No, no, 15.015.
Okay. 15.015. Okay.
Yes.
Just 15.015. This is you are saying.
Yes, it is meter cube of air per meter cube of fuel. It is a air fuel ratio basically.
Yeah. So this is
We have
dimensionless.
calculated.
This is dimensionless. Dimensionless, right?
Hmm.
Okay.
Now we have to calculate the stoichiometric one. So for 1 meter cube of fuel, it requires around how much? 6.5 meter cube of air. Oxygen we require.
See, wait. You are saying stoichiometric. Suppose that
H10.
C4H10 O2 plus 3.76 mole of N2. Now if it will react, it will form 4 CO2 plus 5 H2O.
Sir, it is A plus X by 4. That is
6 point
directly we can able to obtain that
6.5 into
6.5.
3.76. 6.5 into 3.76. 3.76. So it will be 24.44 mole of N2.
Yes. So total, sir, it requires 30.94 meter cube of air if we want to burn 1 meter cube of butane.
6. You are saying 6.5 into 3.76.
Sir, 6.5 plus 3.76 into 6.5. That will be the
Yeah.
total volume of the air
Yeah.
that will be required.
1 meter cube. 1 meter cube of C4H10 will require 6.4 into 4.76 meter cube of air. Yeah, that is
Yes, sir.
true. Yeah,
And
that is true. Yeah,
and
this is
sir,
for stoichiometric.
yes.
Yes, that is true. Yeah. Now, percentage of stoichiometric air that has entered. So this is the stoichiometric. Now you know the amount of air that is the amount of air, volume of air.
Hmm.
So here you are saying like volume of air. Okay. So here volume flow rate of air upon volume flow rate of fuel is equal to the volume flow rate. Here this you are getting 15.015.
Sir, 48.54 is the answer, I think. So around it is 47.96
Yeah. That is correct.
percentage,
That is, I think that is correct. Yeah.
because I have calculated the equivalence ratio, that is a theoretical air fuel ratio upon actual air fuel ratio, and it comes down to be something like 2.06 something. So 1 upon 5 into 100, that will be around
Wait, wait, wait.
48.54.
Harth, I don't think you need to calculate equivalent ratio here. Why you are calculating the equivalent ratio?
Sir, because it is asked the percentage of stoichiometric error, that is the percentage of a theoretical error that is required.
Okay. So now
It is in,
you have that volume of air upon volume of fuel.
yeah, that is a theoretical one, and we are
This is
having the
this is
actual volume.
see this is okay, okay. See, I'm not getting like why you need to calculate the equivalent ratio here.
Sir, sir, it is the same track that we used to calculate in
Okay,
the equation of the that combustion, the balancing.
okay.
So it is
Okay.
percentage of theoretical error which is being asked here. So I have to anyway I have to calculate the phi value,
So okay.
and then 1/5
Now
will,
wait just for 1 minute. The volume of air. This is this is actual, right? This is actual. This is
yes,
actual, right?
yes sir, yes
Volume
sir,
of air, volume flow rate
yes,
is air 15.015 into volume flow rate of fuel.
yes sir.
So you just calculate the volume flow rate of fuel. Volume flow rate, they have given 20 kg per second. So what is the volume flow rate? Sorry, they have given
2
2 kg
kg.
per second. So
Sir,
volume,
it is a mass flow rate, sir, not a volume flow rate.
it is mass flow rate. So you calculate the volume flow rate. From here
Uh,
2 kg. Now just divide it by density. You have already calculated the density. That will give the volume flow rate.
sir,
You want to say something?
no, 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 sir. Density of fuel is 0.143.
This you are saying, right?
No, 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 sir. Not it. It is not 0.143. It is.
See, density is equal to the P upon RT.
It is, sir, 6.997 kg per meter
Just
cube is the density.
okay. I will calculate. Just give me a minute. This P is equal to the 1 ATM they have given 101.325 upon 8.314 into 58, right?
Yes, sir.
Yeah, 58 into 300. Temperature they have given 300. So you just calculate the density from here.
2.35.
This is coming 2.35.
Hmm.
This is coming 2.35
Hmm.
kg per meter cube.
Yes, sir. Kg per meter cube.
Okay. So here you so here you will get the volume 2.35. So the volume flow rate of fuel will be 2 upon 2.35. What will be volume flow rate of fuel? 2 upon 2.35.
0.851.
0.851. This is the volume flow rate of fuel.
Meter cube per second.
Yeah, meter cube per second. Now this is the volume flow rate of fuel. This is actual, right?
Yes, sir.
Now we need to find this is actual or where is theoretical.
It is theoretical. We have calculated based on the equation or the balancing of the equation, stoichiometric.
See, this is for 1 meter cube, and this is 0.851 meter cube per second.
Sir, this is the actual flow rate of the fuel.
Yeah,
This is VF actual.
Actual. Now we need to find that. percentage of stoichiometric error means actual upon theoretical into 100. That what we need to find.
Yes, sir.
So this
We have to multiply this by 15.015.
yeah. Here we need to multiply volume of air.
It turns around to be, sir, 12.78.
15.015 into 0.851, so it will be 12.77.
Yes, sir.
This is the
778.
volume
So
flow rate of air.
this is the actual one.
Yeah, 12.77 meter cube per second. This is actual, and what is theoretical?
Theoretical is 30.
See, theoretical is 6.4 into 4.76 into 0.851, right? No, that is, this is actual. This is actual. Now volume flow rate of air theoretical. Theoretical it will be 0.851 0.851 into, see, 1 meter cube. Theoretical 1 meter cube will require 6.4 into 4.76 meter cube of air.
Sir, why we want to multiply it with the 0.851?
Okay, I will come to that point, please wait. 6.4 into 4.76, 6.4 into 4.76, 6.4 into 4.76,
30.94 into 0.85.
6.4 into 4.76, so it will be 0.851 0.851 into 6.4,
26.32.
it is not 6.4, it is 6.5, bro. It is not
Huh?
6.4.
It is
6.5, 6.5 into 4.76, so what it is, 0.851 0.851 into 6.5 into 4.76, 4.76, so it will be 26.3299, 26.329.
9.
Okay, so now you was asking something, why to multiply with 0.851.
Yes, sir.
See, we want to calculate the theoretical air required for this amount of fuel. No, see,
Okay, so
this we
okay, so
calculated for 1 meter cube.
yes, sir. So 4.815 meter cube, how much is the air required?
See, your question is 4 point.
No, no.
Yeah.
That is for 1 meter cube, if it requires 30.94 meter cube of air. So for 815 meter
See,
cube, how much air is required?
wait. Yeah. So that see, 30 means 6.6. This is 6.5 into 4.76. You are saying, right?
Yes.
This 6.5. So what is 6.5 into 4.76? What is this? 6.5.
30.94. 30.994.
Yeah, 30.94. Yeah, that is why I'm saying for 1 meter cube, 30.94 meter cube of air is required. So 0.851, how much is required?
Okay, yes. I got it now.
So that is why I have multiplied it this, and now you calculate this upon this into 100. 12.77 into 100 upon 26.329.
48.51, sir.
48.51.
Sir,
48.51. That this is what you are getting.
yes, sir.
12.77 into 100 upon 26.329. 48.5. And answer they have given 43.
Sir, the way I calculated before, it is same answer that we are getting by your method. What I did, we found the actual entrainment of the air, and for 1 meter cube, we record 30.94. So anyway, sir, it is meter cube per meter cube is the unit. So if we take the
See,
ratio of the ratio, it won't be
uh,
bother much.
see. Has if you speak like that, I won't be able to guess now. See, please wait. Like, see, like where we have done. Like, there may be some mistake that we can find here. So you see that
Okay.
because answer is very close. So it may be like they are taking something else. We are taking something else. So they are getting 43. We are getting 48.
Yes, sir. Sir, actually, what
Yeah.
I want to discuss is
Yeah.
in the assignment 4, we the question we solved. Okay,
Yeah.
there was a one question,
Yeah. Yeah.
and for that, the answer they have given as a incorrect. So these are the some of the discrepancy that is happening.
Yeah, yeah. See, it may be. Yeah, see. The thing is, suppose that one thing I can say, suppose that we are taking the mass of air is like molecular weight of 28.8. They may have taken 28. They may have taken 29. So that may change something.
Yes, sir.
So this thing may be there. 4.76 air it is. So did you calculate this correctly? 15.015 E.
Yes, sir. Sir, if someone who he has also calculated parallel to of, then we can able to verify.
Yeah, yeah.
So okay, sir. I will recalculate it after this session. Uh,
Wait. Please wait. See, I think what you have done the mistake here. It is not 15.015. It is
okay.
not 15.00. This is just a calculation mistake. See, here you can see you recheck it. It will come somewhere around 13 point something, 13.39. See,
Third.
I will calculate. I will calculate. Just give me a minute. See here, density of butane upon density of air. Density of butane upon density of air, 28.8. 28.8. See, it will be 28.89. So 58 upon 28.8. 58 upon 28.8. 58 upon 28.2.013. See, I think if you take 28.89, that will give us the correct answer. 28.89, that will give quite accurate answer, I think. So okay. So like within 5% limit, our answer is correct. So maybe if you recheck it, you will get the correct answer.
Sir, what is the value of E?
Uh, E is, see how I calculate it is like I am getting E is equal to the, please wait. Okay, I will calculate one more time. No problem.
Sir, 13.45.
Yeah. Now if you get E 13.45, then you will get the correct answer, I think.
Okay, sir. Okay.
Okay, so that is there. Like just calculate E. R is 2.0.5. You say that E will be 0.5 into 2 point 2.0 2.01, right? Earth
Yes, sir.
into 0.5 into
$400.
that will be 20 20 to 20 whole square upon 0.5. No, 20 upon 1
Sir, it
whole
is
square
400.
to the power 0.5
Sir,
minus 1.
400. Sir, it is 400 totally.
Not 400.
We are
400
getting.
minus 1 means 399.
400 is 2.5. That ratio I'm talking about.
Yeah.
400 raised to zero point 0.5 minus
0.5
1.
into 2.01 to the power 0.5 into 399, right?
Hmm.
No, so this is 400 to the power 0.5 means into 19 it will come. It will come 19.
Yes, sir.
It will come 19. So now you calculate this part will be 2.01, 0.5 into 2.01 to the power 0.5 into 19, 13.46. So that is the mistake that you did, 13.46.
Sorry, yes, sir. 43.5. We are getting now 43.5.
Yeah. So if you replace this with like instead of 15, if you take 13, that will give you the correct answer. Okay, guys. So
Yes, sir.
like remaining question we will discuss in the next class. So like two three questions are remaining that they will discuss. We will discuss in the next class. So Manish, hello, yeah, Manish, are you there?
Yes, sir.
Yeah, Manish. So this question, is this question clear to you?
Yes, sir.
So if not, you tell me. Next we will discuss this question also. No problem.
Yes, sir.
So if you try to solve. If you are not getting, you tell me. We will discuss this question. Okay. So now we can leave. Okay, guys. Thank you.
Okay, sir. Thank you,
Thank you,
sir.
sir.